I'll record this and do my best to post it to the L YouTube channel. All right. So let's pick up where we left off by taking a look at these synthesis problems. The first one, we're making a halohydrin. And the only way we know how to make a halohydrin is from an alkene. And what else? Well, we're starting with acetylene, and we have to add 2 carbons. So the first thing that we're going to do is we're going to add the 2 carbons to our acetylene. So we're going to treat it with sodium amide in the first step, followed by ethyl iodide in the second step, and that is going to give us this compound. Now we can reduce that to the alkene, and the way we do that is with hydrogen and Lindlar's catalyst. That's the only way to do that. You can't use sodium metal reduction to reduce a terminal alkyne. And then for the last step, to make the halohydrin, we just treat it with bromine and water, and we are done. Okay, let's make sure that we keep these separated. Okay, so for the next one, we want to make a primary alcohol. And in terms of my retrosynthesis here, I'd say, well, I could make it, I've got a couple options really, but I think the best way to make this would be from this alkene, right? And then I could just do an anti-Markovnikov addition of water. And we also discussed this, that if you're starting out with an alkane, the only possibility that you have for the first step is to treat it with bromine and light, and that is going to give you the tertiary alkyl bromide. And so we can just treat that with a hindered base, like potassium T-butoxide, and that's going to give us that Hoffman alkene that I have in blue here that I want. And so the last 2 steps are going to be nothing more than hydroboration oxidation. So borane and THF, followed by hydrogen peroxide and sodium hydroxide, and we are done. All right, didn't give myself a lot of room for the last one, so I'll squeeze it in over here. Oops, no, not like that. Here we go, this guy and this. And then we're going to make an alkyne. Well, the only way that we know how to make this alkyne, if we're doing a retrosynthesis, is to make it from the alkene, right? Because if we have this alkene, we could make the dibromide, and then we could do the double elimination. So we have to make that alkene. And so the first step certainly has to be treatment with bromine and light. So bromine and light, and that will make the tertiary alkyl bromide. And somehow we've got to move the bromine over to this position and do a Zaitsev elimination. So let's treat it with an unhindered base. Oops. Sodium ethoxide or sodium methoxide, either one is fine. Oops. And that would make this alkene. And then if we do an anti-Markovnikov addition of HBr, then we can move the bromine over into this position. And then we can just do an elimination using a hindered base like potassium T-butoxide to give us the Hoffman alkene. After that, we can make the dibromide by treatment with bromine, and that will make the dibromide. I'm kind of running out of space here, but I'll do my best to scribble it in. And then the very last part is going to be treatment with excess sodium amide, and then treatment with water in the end. Excess bromine and light. No, you couldn't do it in this specific case, because if you did excess bromine and light in this one, what I imagine would happen is that since you've only got one tertiary proton, right? This is the only tertiary proton that you would have. Oops, is this one here. So if you did excess Br2 and light, you would brominate at that position, and then you would start brominating here. All right, and you couldn't do a double elimination on that to get the terminal alkyne. Does that make sense? Yeah. Okay. Yeah. No, it's a good idea, but I don't think it would, or it wouldn't work in this case. All right. So A part that we don't really spend a lot of time on, and it says skip, but I don't like the idea of skipping this. Why? Because it's 2023 is the year, so we're in 2023, and I think that I would be remiss as your instructor if I didn't talk about how to make chemistry a little more environmentally friendly. If you think about it, chemists, can create a lot of nasty waste when they do the reactions. I mean, you just think about the reactions that we do. I mean, you're using mercury and osmium. These are dangerous chemicals. And so the tenets of green chemistry are shown here. The first thing we want to do is prevent waste. If we can avoid making waste, that's a good thing. And of course, if we can use something that's not hazardous, I would definitely choose that, right? If you can avoid using osmium, I would do it, right? Use safer solvents. So that means trying to eliminate things like dichloromethane. And this is a solvent I used a lot when I was a chemist working in industry. Chloroform, carbon tetrachloride, CCl4. Like, let me just tell you for an example, okay? I've I have only used, I mean, I worked as a chemist for 15 years, and that doesn't include graduate school and working as an undergrad. I've used carbon tetrachloride maybe a couple times in my entire life. But my first office mate in my first job in industry, they used to wash their hands with this, okay, to get them really clean at the end of the day. And so, this is something that was regarded as somewhat innocuous back in the day in the 70s. And we've since found out that it's carcinogenic and quite dangerous. And so it's very difficult to even find carbon tetrachloride now. So we want to try to avoid using solvents like this and chloroform. And then dichloromethane. Dichloromethane is still readily available, but what you'll find is that chemists are trying to find more and more ways to phase it out. So we're always trying to find ways to make our chemistry a little bit safer in terms of our solvents. And then atom economy. So it says here, maximize atom economy. And you might be wondering, what the heck is atom economy? This was developed by somebody named Barry Trost. And he I think he was at Scripps Research Institute, and he developed the idea of atom economy. And it just says here to use reactions where most of the atoms in the reagents are incorporated into the product. And if you're wondering, what does that mean exactly? Well, here's an example of two reactions. One has a good atom economy, and the other one has a poor atom economy. So if we look at the oxymercuration demercuration process shown here on the top, that's a Markovnikov addition of water to avoid a carbocation rearrangement. But theoretically, you could just use it to do a Markovnikov addition like is being shown here. But look at all the atoms that are highlighted in red in the reagents. These are atoms that don't end up in the final product. They end up in the waste. And so we say that this reaction is a poor atom economy, whereas the one below, use an acid catalyst here, and you can see that almost everything ends up in the final product. And so we say this reaction has a very good atom economy. And so this is something chemists consider all the time nowadays, is does this reaction have good or poor atom economy? Other things that we can do are use catalysts, right? Because catalysts regenerate. So instead of using stoichiometric amounts like 1 mole and 1 mole, we'll use 1 mole of the substrate and maybe 0.1 moles of the reagent, right? So we use less reagents. Energy efficiency, this isn't something I've thought about a lot, but you can imagine that if you're heating a reaction mixture, if you can avoid turning up the heat for days on end, let's say you have to reflux it or something, doing the reaction at room temperature is going to use less energy. And then, of course, renewable feedstocks, right? If you can find some kind of starting material that is renewable, that's going to be better than using some kind of petroleum-based starting material. So there you go. So that's what green chemistry is. And if you just do a quick Google search on green chemistry, you can find all kinds of interesting articles about it. It's a very hot topic in chemistry these days, and you can imagine why, because again, everybody's kind of in the get the mindset of trying to find ways to protect the environment. I enjoy the environment, so I want to protect it. I think green chemistry is a great thing. Now, section 11.7, I would say that this section is more of an FYI, right? It says increasing your proficiency in synthesis. Well, I mean, that could differ from person to person. The main thing is just to remember all the reactions in 11.1 and 11.2. And then, it says you're creating your own synthesis problems. I don't ask my students to do this, but you can imagine that if you started with something simple And then you just keep doing reaction after reaction. You could give that to a friend, and then they could try that same kind of thing. So let's say you started with acetylene, then you alkylate it with a methyl group, then you add another one, you do a reduction to make a cis-alkene, right? Then you could say to your friend, well, how would you do this? And you already know the answer, right? Anyhow, it's something you could try. But again, I don't ask students to do that. And then this is something that you're going to see more and more as the class moves on, is that we'll have more and more different ways of doing the same synthesis. So if you take a look at this one here, I mean, you can see that this is clearly just an anti-Markovnikov addition of water across a double bond, but you could also do an anti-Markovnikov addition of HBr to make the primary alkyl bromide like this. And then you could do, oops, that doesn't look very good, like this. And then you could do, son of a gun, I'm missing the carbon. Where is it? There it is. Okay. And then you could just do an SN2, right, in the next step. So either one is fine. Both are perfectly acceptable. And we actually saw another example of that earlier today. So that covers all of chapter 11.